I guess my, what? There's just 3 sections, one more section after this one. So, yep, comprehensive. I don't know. It'll be more than 100 points, but I haven't decided what I'm quite going to do. I think when is the final in here? It's like Wednesday 8. Wednesday 8. Wednesday, yeah. Yeah. It's Wednesday 8 to 10, right? Yeah. Okay. On page 177. We'll look at 12. Oh. Okay. So, all right. So 12 says -1, 2, 3. Okay. Probably rather than doing 2 cofactors, what I'm going to do is I'm going to multiply the 4th row times 2 minus 2 and take it up. So, because you can use anything you want with this one to do it. And if I multiply and add it to a row, I don't change the sign. So I'm going to multiply the bottom row by -2 and take it up. So that'd be a -8 and a 3. That'd be a 0. That'd be a -2. And then that's a 0. 4, 2, 4, 3. Now what I could do is I can expand by that the 4th column, and so that's going to be a -1, and it's 4 plus 4, and then it's 3. The cofactor is going to be a -1, 2, 3, 3, 4, 3, and a 3, 0, -2. Boy. What do I want to do? You know, if I think I can get that diagonally. I take the first row, -1, 2, 3, and I'm going to make a triangle matrix. I'm going to multiply the first row times 3, add it to the second. So I'll go 0, 6, 10, 9, 12, right? And we multiply the first row by 3 and add it to the third row. So that's 0, 6, 7. Dang it, didn't do what I wanted to. Okay. I guess I'd go ahead and expand it by that first one. So it's a -1. And then the cofactor is 10, 12, 6, and 7. And I'll just go ahead and do that determinant. So it's 3 times a -1. And then it times a quantity 70 minus 72. 3 times a -1 times a -6. So that should be my answer. Now you can do, you can do any way you want with that, so. Okay. Be fun to grade them. It'd be like simultaneous solutions of linear equations with four equations, and I hated those problems. You ever do problems like that? People can. This is why matrices is better, because you can see it. But when you simultaneously solve them and you eliminate, it depends on which equations you take, how it eliminates. And if you have 10 people in the class, you know you're going to get 6 different ways they're going to do it. There's just no standard way of being able to write something up so you can check their answers. That means that when you do those kinds of problems on the test, you just have very few of them. 0 minus 2 minus 4, 0, 3, 5, 4, 1, 6, 5, and a 0. I think I'm going to try to get a diagonal and get that diagonal so that I have zeros below the diagonal. Then I can just go product down the diagonal. 1, 5, 4, 1. 0 minus 2 minus 4, 0. I'm going to multiply the first row by minus 3 and add it to the third. 0 minus 15 is a minus 10. Minus 12 is a minus 8. Minus 3, minus 2. Wow. 6 times the first row. 0. 35. 24 and 5 is 29. 6. So if I multiply 2 times the second row, 1, 5, 4, 1, 0, minus 2, minus 4, 0, minus 5 times the second row, right? Dang it. 0. How to make that 0? Minus 5 is plus 20, plus 12, minus 2. 0. I hate this. So what am I going to have to do? I'm trying to get that diagonal. Do you think there is? Yeah, 20 is the answer. Well, as long as I'm on this route, I just will finish it. I'm not going to do that, what I started out to do. I'm going to get the cofactor, minus 2, minus 4, 0, 0, 12, minus 2, 35, 29, and 6. So I got myself a big mess, don't I? What did you do? Oh, I see. You worked on this column over here. I certainly went down a path that well, let's just see what happens if I continue on with this. Minus 2, minus 4, 0, 0, 12, minus 2, and then take that 2 times 35 over 2, right? That'd be 0. That'd be 70, wouldn't it? 70, 29, 41, and then 6. Is that right? This one's subject to a lot of... Now I have to get rid of that 41. Zero, 12, minus 2. And I could go, if I did a negative 41 over 12, and make this 0. Ooh, what would that make? Minus 2, I'd make that a 6. And is it going to come out right? Plus 6. Third, 6 over 6. Boy, I certainly made it hard. 77 over 6. Is that right? It isn't coming out right. Because the answer is 20. Let, let's go back and do it your way so we have it done right on this. So, what is it? 14. We got 14. It's 1, 5, 4, 1. And so he just took the first row and subtracted it from the third. 1, 5, 4, 1, 0, negative 2, 0. So that's a 2, 0, 0, right? 0. Okay, minus 6, 5, 5, 0. Then you expanded. You took the 1 on top and then the cofactor. So it's 0, minus 2, minus 4, 2, 0, 0, 6, 5, and 5. Then you just do 2, let's see, it's got to be a minus 1 times second row, first column, 2 cofactor, minus 2, minus 4. Is this what you did? Or?
Yes. You forgot to include the first cofactor because
Well, that's 4 plus 4.
that's 4 plus 4.
1 plus 4. Okay, first row. Okay, so this is negative. And this is a negative. So it's plus that point. So then it's minus 2, and then the minus 10 plus 20. Is that right? Plus. We're still not coming up with 20. Oh, yeah. So this is 2 times 10. Okay. Ooh. So let's see. So number 16. 16. A, B, C, 5D, 5E, 5F, G, H, I. So what we can do, we can factor that 5 out of that second row. A, B, C, D, E, F, G, H, I. When we do that, it says at theorem 3, says if we 3C says if one row of A is multiplied by K to produce B, then the determinant of B equals K determinant of A. So there's no change in the sign. So then this is 5, and the determinant of that is given to you as 7, right? So this is 35, because I gave you the determinant of this thing right here. It's 7. Okay. 18. B, E, F, E, B, C, and G, H, I. Now if we interchange row 1 and 2, A, B, C, D, E, F, G, H, I. And if you look at theorem 3, and it says theorem 3B, says that when you do that, you have to put a minus this. And then we know that determinant is 7, so then that's a minus 7. So that's that one. Okay. 20. This is A, C, B plus 3G, E plus 3H, F plus 3I, and GHI. And then that theorem 3A says if you multiply one row of A is added to another row to produce the matrix B, then the determinants are the same. So this is equal to the determinant of A. That A, B, C, D, E, F, G, H, I. And that thing was given to you as 7. And that's theorem 3, and that was A. Hmm. What? Says use determinants to find out if the matrix is invertible. Well, this one, if the matrix is not equal to 0, it's going to be invertible. And that's that theorem 4. It's on this thing. So the square matrix A is invertible if and only if the determinant is not equal to 0. So all you got to do is take 22, do the determinant of it. Now it has to be square, matrices, and that's what that theorem 8, that invertible matrix theorem, all square matrices. Okay. What's the best way to approach this? The second row times 5 and go up. So it's 0 minus 15 and a minus 5, right? So that's a 16. So that's 10, and that's a 9. 1 minus 3 minus 2, 0, 5, and 3. So then if we do a minus 1, second row, first column, and then this is going to be 16, 9, 5, and 3, which equals a negative 48 minus 45 minus 3. Okay, so it's a minus 3, then by theorem 4, this is on page 175. Gotta go back. 173. It says a square matrix is invertible if and only if the determinant is not equal to 0. Matrix is invertible. Okay. 24. It says use determinants to decide if the set of vectors is linearly independent. Okay. So what we're going to do is we're going to take the determinant, see whether it's invertible, and then if it is invertible, then you can use that theorem 8, that invertible matrix theorem, to determine, say that the vectors are independent. If it's not 0, if it's equal to 0, then they won't be independent by that theorem 8. So 24. So I go 4. And I'm just going to take those vectors and put them in a matrix. 6, 2, minus 7, 0, 7, and a 3, minus 5, and a minus 2. What do you think? Take the first row times 1 and add it to the third. So that'd be a 4 minus 7 minus 3 6, 0, minus 5. We're just straight adding, right? So 6, 0, minus 5. But we just, well, those are not independent because that first and the third, second and third row are the same, right? If we took 1 times, I mean, it's going to be, it'll just be 4 minus 7 minus 3. Took a negative times this row and added it to the third row, we got zeros, right? So the determinant is going to be equal to 0. And then if the determinant equals 0, then theorem 4, the matrix is not invertible. And then if you go back to that theorem 8, back in that first chapter, I think it is, 8a will lead to a conclusion that theorem 8e is true and the vectors are linearly dependent. So that's theorem 8. I should have brought that sheet that I printed off for you. What page is that on? Is that the first chapter? Did you find it? 100 what? Yeah. See, and if you look at 8a, it says A is invertible, so it's the not of that, right? It's not invertible. And E says the columns of A form a linearly independent, so the columns of A form a linearly dependent set. Because remember, it's either true or can be not true and not true for everything. Yeah. Okay. What's that? Okay. We'll do another one of them things. Do 26. And I'm just going to do the determinant, write that thing out. 3, 2, minus 2 and 0. 5 minus 6. Minus 1 and 0. Minus 6. 0. 3 and 0. 4. 7. 0 and minus 2. So should we just do the cofactor on that fourth column? This is a minus 1. It's 4 and 4, right? So that's a plus. And it's a minus 2. Cofactor is 3, 2, minus 2, minus 6, minus 1, minus 6, 0, 3. What do you want to do with that? It wouldn't be too bad if we took the first row times 3 and added to second, would it? Then we could get that minus 6 to 0. Would, that's a minus 2. 3, 2, minus 2. And I said first row times 3, right? 9 and 5, 14, 0. 6. So that's 5, isn't it? Minus 6, 0, and 3. Did I do that right? Oh. Let's see. Okay, yeah. So this should be minus 7. Now then it's a minus 2, and then it's a minus 1, because I'm going to go first row, second column, times 2, cofactor, 14 minus 7 minus 6 and 3. Right? That's a minus and minus, so this is actually 4, right? Because that, and then this is 42 minus 42, isn't it? So that's 0. So this is the same deal as the last one. It's a okay. Let's look at 28. It says if 3 row interchanges are made in succession, then the new determinant equals the old determinant. Is that a true or false statement? Every time you do a row interchange, that theorem 3 says what do you do to the sign? Yeah. And so you're doing 3 minuses, so you're getting a negative. So that's false, right? Okay. So A is false. A false. There's 3 sign changes, right? And that's on that. What was it? That was that theorem. I think these are all going to relate back to that theorem 3. And B. So B says the determinant of A is the product of the diagonal entries in A. Well, you have to have it as a triangle matrix. Then it's diagonal, right? If you can't just take it times the diagonal without getting zeros in the bottom. So this is false. That's you must have triangle matrix. Okay, C. I don't know what theorem that is. I guess another way of calling it, you could have it in echelon form, right? C says, if determinant A is 0, then two rows or two columns are the same, or a row or a column is zero. So if two rows, if two rows are zero, you can interchange them so that you couldn't get a diagonal of your. So I think that's false. If the determinant is zero, then two rows or two columns are the same. I think if you had a column zero, your determinant would be zero. I don't think a row zero.
No, I think they have
What?
I think they, so I think we went over and then that is your, this matrix, two rows of columns are not the same, and, rather than either one of them is zero, one of them is zero, but
A row of zeros, I think when you have rows of zeros, it doesn't do it, but a column of zeros will do it, because then when you tried to get your diagonal to be, a reduced echelon, you would have a zero in one of those spots, but a row wouldn't give it to you. I think it's false. Okay. D. D. The determinant of A inverse equals a negative. Negative the determinant of A. And that's false. Because it's false. Because the determinant of A inverse equals the determinant of A inverse transpose. It's not equal to the negative determinant of A. Then 30 is saying what? Use theorem 3 but not theorem 4 to show that if two rows of a square matrix A are equal, then the determinant A equals 0. Same is true for two columns. Why? Okay. Okay, so if two rows are the same, then the determinant, if you swap a pair of the rows, if swap the two rows, then the determinant of A has to equal the negative the determinant of B, don't it? The swap. But they'll be exactly the same, but A equals B yet, so the determinant of A equals the determinant of B. You know, the theorem says that this is what should happen, that theorem 3B says that if you swap a pair of rows, then the determinant of A has to equal negative determinant of B. But if A equals B, then the determinant of A equals the determinant of B. And so, what have I just did? So then the determinant of A has to be equal to 0. Because that's the only way it could be true. Okay. Well, we have 2 more periods.